Good morning, good afternoon, good evening, ladies and gentlemen. Welcome to my presentation on end-to-end learning in optical fiber communications, concept and transceiver design, which is joint work with Boris Karanov and Paulina Bayvel from UCL. So in our presentation, we're talking about machine learning and the application of machine learning to optical communications. And we all know that machine learning has seen tremendous successes in the past decade and especially in the past few years. And one of those drivers for this success was image recognition and computer vision, where we now have seen accuracies that surpass human performance. Machine learning systems can recognize images and objects in images better than humans can since a few years. So it's quite natural to ask ourselves, can we use machine learning as well to help us design optical communication systems? Communication engineering as a discipline has been around for 70 years, following the seminal guidelines and the seminal work of Claude Shannon. And these 70 years of communication engineering have brought us very close to the theoretical limit. But this is only true for a subclass of communication systems. We still have quite a lot of systems that we use on a regular basis where we don't know good algorithms for reaching the Shannon limits or where we don't know optimal transceivers. So very natural question to ask is, can machine learning help us to identify and learn novel transceiver concepts and novel transceivers? And in this talk, I'm looking at the concept of using neural networks to help us learn optical communication systems. And actually, this is part of a two-talk series. So by luck, my PhD student Boris Karanov also got invited for a talk. So we decided to split our work on two presentations. So in this talk, I will briefly talk about the basic concept and design guidelines, and Boris will talk about experimental demonstration, future topics, and an outlook in his presentation that's given on Thursday. So what is a neural network? We're talking about neural networks here, and I'll just give a whirlwind tour of neural networks. We're looking at something called feed-forward neural networks, and a feed-forward neural network is actually a very simple device. It's a device that takes a vector of dimension m at the input and maps it to a vector of dimension n at the output. And it does this by using a layered function or an iterated function. So each of those layers that you can see in this neural network representation corresponds to one simple function. And you just keep on repeating those functions on the input, then on the output of the first function, second function, and so on until you reach the output. How does such a function look like? Well, it's a very simple function. So we apply a linear operation to our vector. So we take our input vector v, we multiply it with a matrix w, and add an offset vector b called the bias vector. And then the most important thing comes. We apply a nonlinear function GNL. And this nonlinear function is essential for the expressive power of those neural networks. By using this nonlinearity, we can express essentially every possible, or we can approximate every possible system by a neural network. How does such a nonlinear function look like? Well, a very often used function these days is the so-called rectified linear unit, which is kind of like a diode function. So the output is 0 for negative inputs, and the output is just the input for positive inputs. Or you can extend this with an exponential function, the ELU. Then it's called the ELU function. So it's a very simple nonlinear function. And with this, you can approximate any system that takes an input vector, maps it to an output vector by properly choosing those matrices W and B. So all the expressive power sits in these matrices W and B, which you choose such that your neural network approximates a certain function. So the objective of learning is to find those parameters W and B such that you optimize an unknown system. How does this work? Well, in order to work, we need to define a loss function. This loss function L depends on those parameters W and B, and it's essentially comparing the output that the neural network generates with the desired output. So you have a so-called training data set S. This training data set contains inputs to your system, vectors V0, and it contains desired outputs. Desired outputs V tilde. So what you do is you take your input, you process it by the neural network, and you compare it to the desired output. And you can use your favorite loss function, for instance, mean squared error. And then you just take the average of the loss functions. So that's how it works. How do you find those parameters W and B? Well, we use something that you know from digital signal processing. If you have implemented the CMA algorithm, for instance, you use a technique called gradient descent. You have a loss function that is the distance to the unit circle, and use gradient descent to optimize the parameters of your algorithm. And that's the same we're doing here. So we use gradient descent. So we take the gradient of our loss function with respect to the individual matrices W and B, and then we subtract an epsilon of the gradient from our W, and then we keep on iterating this until we converge to a solution. And the main thing is that we use something called a computational graph to express our loss function. So our loss function depends on the inputs, V. It also depends on W, B, and you can draw this computational graph, and you can use the chain rule of calculus on your computational graph to find the gradients with respect to the different W's and B's. And every function that you can express as such a computational graph can be used inside neural networks to optimize your functions. So how can we use this in communications? Well, the most natural thing to do is first try to apply this to the receiver. So you have a transmitter, transmit a message M, generate a waveform of symbols X, receive Y, and then you apply it to your receiver, trying to guess an MT, so you get an M hat that approximates your transmit symbol as close as possible. So you could, for instance, transmit a pilot sequence M, you have received data, and you put your received data into the neural network, and the output of the neural network should be the transmit symbols, MT. So this has been proposed on multiple occasions already for optical communications. And we're looking at an example of an AWGN channel. So if you like to play around with this, we provide source code using the PyTorch library by Facebook. You can use the QR code to get to our GitHub page where you can find the source code. And we use a 16 QAM constellation with a AWGN channel, and we learn the decision regions. And you can see that it's not a difficult thing to do. And after some iterations, the neural network can approximate the decision region of the 16 QAM quite well. So this is a little bit boring, and it doesn't bring us closer to our goal of designing actually communication systems. So what we can do is we can take a look at a concept called autoencoders that's used very frequently in the field of machine learning, especially for parameter identification, for dimensionality reduction, or for image compression. An autoencoder essentially consists of two neural networks, an encoder network and a decoder network. And the goal is that the decoder reconstructs V as close as possible. So it generates a V hat that should be ideally equal to V. And it does so by going through a bottleneck. This is the so-called bottleneck. So what you can do is you can often use this in an unsupervised way. So you have some data V, and you want to find some low dimensional representation of this data. Then you can use it. So this autoencoder concept looks very similar to a communication system. In a communication system, we have a bottleneck, which is our channel. The communication channel is our bottleneck. So we want to transmit data V over our bottleneck and reconstruct them as close as possible. And as this resembles a communication system, it has been recognized by Timo Shi that we can implement a communication system using such autoencoder concepts. So in fact, it means that we replace the transmitter and the receiver by neural network, and our channel by a computational graph that is differentiable. And then we can do the learning from end to end. So our input to the system to loss function is M of t. We calculate the desired output of our neural network, and we compare it with M of t to see if M hat resembles MT as close as possible. The only constraint that we have is that our channel needs to be differentiable. So we can look at an AWGN channel, y is equal to x plus n. The noise is independent on the parameters W of the transmit network. So when we take the derivative of the noise with respect to the transmit network, it's just 0, so we can neglect the influence of the channel. So what we can do is we learn a constellation. And here we do this. So we learn the constellation in our transmitter and the decision region in the receivers jointly at the same time. Again, if you want to play around with this, we have the source code online, so you can download it and generate the animation for yourself. And we see that the constellation learns and converges to something that looks like being extracted from a lattice, which we know is very good on the AWGN channel for optimizing the symbol error rate, depending on, of course, the signal to noise ratio of your channel. So you see that this works quite well, and we can actually learn a nice constellation. The very nice thing about this is once you have this neural network at transmitter and receiver, you can just replace your channel model. You can replace it by something more complicated. For instance, in ECOC 2018, it has been proposed to use a zero-dispersion optical fiber model, where you have small steps of only nonlinearity followed with distributed noise. And we can just plug in this zero-dispersion channel model, which is a little bit far away from practice, but it's a very good thing to visualize. The nice thing is this is computationally different. This computational graph is fully differentiable, so we can just use it. So let's see what happens. Again, you are welcome to play around with this. So we have some random initial constellation, some random parameters of the received network, which give decision regions that are completely useless. But once you're learning, you see that the constellation points, they move, and the decision regions are optimized at the same time. And you will see that here it's a more complicated channel model, so it takes a little bit longer to converge, but you will converge once, and you have decision regions matching your symbols, and the symbols are optimized such that the decision regions are well separated. So pretty nice. So then what we intend to do is we intend to apply this to a different channel model. So in our work, we applied this to a channel model that actually has dispersion, which will complicate things, as we'll see soon. And we apply this to multidimensional constellation for IMDD links. And this has been applied in this end-to-end auto-encoder concept, has been applied also in different contexts in optical communications. For instance, applied to nonlinear Fourier transform, for constellation optimization, for geometric shaping, but also including the split-step Fourier method. And there is a very recent paper that nicely explains how you can use this concept also for nonlinearity compensation based on the split-step Fourier method. So what is the channel model that we are looking at? We're looking at this IMDD channel model. And we have a channel where we have a waveform now. So this is the main difference to the examples I showed before. Instead of optimizing symbols, we directly optimize a waveform, because in IMDD, we don't know which pulse shaping may be well suited. So we go directly to the waveform. We do this in an oversampled way. So we need low pass filtering to adjust everything to the bandwidth of our transceiver, of our equipment. We have D to A and A to D converters that have a finite ENOP. So we model these by adding noise. We have Mach-Zehnder modulator, which is nonlinear. We have the fiber. The fiber is dispersion only, so no nonlinearities. And it's simple chromatic dispersion, square law detection, and noise due to TIA. This model is fully differentiable, so we can use it to learn waveforms. So we're just changing the parameters of the neural networks. Instead of symbols, we can directly learn waveforms. So here's the computational graph of the model. You see everything is pretty simple. You have convolutions, which are differentiable. The Fourier transform is just a linear operation. It's matrix multiplication effectively, so it's differentiable. And square law is also differentiable. So everything is differentiable, and you can use this computational graph inside the optimization. Now, how do we build a transmitter and a receiver if we have dispersion? Our first attempt that triggered this work was to use a block-based transmitter. So we have messages at time t-1, t and t. We feed them into a neural network. We process them and generate a vector of a waveform vector. In our case, we had 48 or 24 samples of our waveform, and then we just concatenate those vectors. These are oversampled, so we have a low-pass filter that smears the waveforms so that the effects where you stitch together, they become negligible. So it is over this low-pass filter smearing. So with this neural network, you can pre-compensate at least some dispersion that is inside such a block. Okay, how does the receiver look like? The receiver looks in the following way. Again, we take our received waveform and we just cut out some vectors or some blocks of this, and we process them by a neural network. This receiver neural network has a special type of node at the end. It's a so-called softmax node, which you'll see when you learn about neural networks in more detail. It's a layer that essentially generates a probability vector. So at the output, we get a vector containing the probabilities that our message is either symbol 1, symbol 2, up to symbol capital M. And to calculate the symbol error rate or do the inference finally, we just pick the symbol that has the highest probability and assume this was the transmit symbol. In our loss function, we use the so-called cross-entropy loss, which means we maximize the probability that the symbol we observe is actually the received symbol. So we know which, so it's actually a transmit symbol. So we know which symbol has been transmitted. So we maximize the probability that the receiver generates this symbol. And we do this using a logarithm in front of it. So this is the receiver neural network. Obviously, whenever we have chromatic dispersion, which smears, the chromatic dispersion from the neighboring blocks is not treated. So this is essentially being treated as inter-block interference. So we may see that there is some limitation. So let's see at some simulation results. This is how the whole system looks like. So we put those blocks of neural networks together. We serialize everything, transmit, deserialize, and then have the single blocks so that we can actually get our probability vectors and do the calculation of the symbol error rate. So this is what we get. So we have different configurations of our networks. So the first thing is with M input symbols, so 3 bits mapped to 6 waveform samples. And this is oversampled domain. So it's not that there is some coding inside, but it's just being oversampled. And we see that we are limited in our transmission distance to roughly 40 kilometers at the FEC threshold. What we can do is we can increase the size of those blocks to limit the effect of inter-block interference from chromatic dispersion. Then we can increase the transmission distance by 10 kilometers. We could go further, but the disadvantage is that the complexity increases very unfavorably because of these matrix multiplications that we need to do inside the layers. The complexity doesn't grow very nicely with the number of symbols. So this is actually going to be infeasible pretty soon, and we are limited by chromatic dispersion. So we need to find a way of tailoring these neural networks to the dispersive nature of the channel. This is what we did then in a follow-up work that was published in Optical Express. Here we use recurrent neural networks or bidirectional recurrent neural networks. So the idea is we have the message at time t minus 1 t plus 1. We feed the message into a small neural network, but before doing so, we concatenate the message with the output of this small neural network from the previous step. And we have the same thing in parallel, taking the message from the future. So we take the message that's coming from the future, from the output of this small neural network, we concatenate it. So we have 2 neural networks that are acting kind of like an IIR filter that filter the sequence from both directions. We do some blocking and to have a block size, so have a block-based transmission, but inside this block, we do this bidirectional processing. And at the end, we merge the outputs of the 2 neural networks to generate the waveform. And because now we use very, very small neural networks inside, and we showed that we can use extremely simple and small networks without sacrificing the gains, we have a very low complexity. How does the receiver look like? The receiver looks essentially the same. So we have these 2 structures, these bidirectional structures of small neural networks. And then we add one of those softmax layers, which help us to calculate probability vectors, which we can use then for decision or for the loss function. What we do at the receiver is that we do a sliding window processing. So what we do is we put a window over a few of those stages, and we process them getting probability vectors. And because of this bidirectional nature of the chromatic dispersion, the symbol in the middle will have the most reliable probability vector. But we average this one with the symbols that we get also from sliding the window, where we can capture more chromatic dispersion from the future, but also from the past. So we get actually multiple estimates that we average together. So here's how it looks like. We have a block of data that we transmit, process it by the transmitter, bidirectional neural network, transmit over the channel, and at the receiver, we employ these sliding windows. This also allows us to reduce the latency, and then we get probability vectors, which we average to get our estimates. And this is how the performance looks like. So we can significantly increase the or decrease the bit error and increase the transmission distance by employing these with a windowed receiver. So for window length of 10, we have a distance increase, ridge increase of 20 kilometers, which is quite remarkable. Further increasing the window doesn't lead to significant extra gains, because at some point, eventually will be noise limited. The chromatic dispersion will not be a limiting factor anymore, but because of the attenuation, we'll have so much noise that we cannot just cope with the system. So in our work that we presented at Allerton conference last year, we showed that this can outperform maximum likelihood sequence detection if we have complexity constraints. So it's actually very good in terms of complexity. And we also compare this with a nonlinear processing at the receiver using a neural network approximating a Volterra equalizer, which is shown here. So we have on-par performance at high bit error rates with the Volterra equalizer if we afford quite a lot of complexity. So this is a pretty big Volterra equalizer, over 61 symbols. And we see that we even outperform this Volterra equalizer at low bit error rates. And then we also see that if we employ a Volterra equalizer that has a low complexity, so small one, then we outperform that one quite significantly. So that's the dashed curve here, and then you have a gain at the ABC threshold of more than 20 kilometers. Another question that pops up in these cases, how well does it generalize? We know that neural networks have issues in generalizing. So if you don't take any precautions, it actually doesn't generalize too well. So you take this system, you train it for transmission distance of 40 kilometers. You have a transmitter receiver neural networks optimized for 40 kilometers, and you just apply the system. And then you observe that when you change the real transmission distance just a little bit, the bit error rate very rapidly increases and you get a quite bad performance. But we solved this problem, and we can apply a technique called multitask learning, where we can allow the transceiver to operate on a range of distances without needing reconfiguration. So we can just find parameters of our transmitter and receiver neural networks that are not trained on a distance of 40 kilometers, but 40, let's say, plus minus 4 kilometers. And then we get this bar stub. We take a hit on the lowest bit error rate that we can achieve, but we can operate on a region of 10 kilometers, well below the ABC threshold, without needing a reconfiguration. So this is one set of parameters, and you can just change the transmission distance. It will still work. You can even push this to 40 plus minus 10 kilometers. So you have a range of 25 kilometers over which you can transmit without needing reconfiguration. So this is really a big step towards distance agnostic transceivers. For instance, with OFDM-based or DMT-based systems, you also cannot do this. You have one set of parameters which you fix the distance, and once the dispersion changes, you need to readapt. Here we have one set of parameters. It will work over a range of 25 kilometers. So to summarize, we showed that machine learning can be very suitable in optical communication systems if we don't have optimal algorithms. In order to cope with the dispersive properties of the channel, we use recurrent neural networks, and we get performance that are close to state-of-the-art benchmarks or even outperform them. So as a take-home message, the main very nice thing about machine learning is that we can harness this very vast machine learning toolbox, which is being developed by big companies like Google and Facebook as we speak. Unfortunately, configuring these neural networks still takes a lot of hand tuning with educated guesses, requiring expert knowledge, and therefore end-to-end learning of the whole transceiver is quite an ambitious task to do. And there are still many open problems that need to be solved, and we're just trying to understand the impact of deep learning there. So if you are interested to learn more, to see the experimental demonstration, to see future trends, and to see how you can fine-tune transmitter and receiver inside the experimental setup, you should take a look at a talk by Boris, which is talk TH1D1, and that's going to happen in 2 days on Thursday, December 10th. With this, I'm at the end of my talk. Thanks a lot, and I'm very happy to answer your question. This was joint work with UCL and was supported by Nokia Bell Labs. Thanks a lot for listening.